to all those of you in the room or online to have come back. We have this afternoon a presentation by Alexandre Reiffers-Masson, who is a professor at IMT Atlantique, about the optimal sampling strategy of measurements using different techniques, among which optimization, I think. So thanks, and it's up to you now.
Okay, hi everyone. So it's a pleasure to be here. So about this presentation, it's not exactly about general result and kind of paper. It's more about the discussion of what could be some ways that are related to D-level optimization and differential equation to study the optimal sampling strategy measurements. So please do not hesitate to interrupt me if you are not clear about some details, and perhaps the slide will not be okay. There will be some typos, so please do not hesitate to interrupt me. Okay. So I will start a bit by going back at what we know a bit in the past before kind of machine learning and in statistics, when we want to choose kind of the features that we would like to optimize. And this domain was called at that time experimental design. And let's try to recall the basic model of experimental design. So in experimental design, what you assume is that you have multiple measurement strategies for a signal. And every time you are using a given measurement strategy K, and you have n possible measurement strategy, you get a multi-dimensional output, y of k, which has the following form, right? So y of k is equal to a of k, which is kind of the measurement matrix, x, which is the hidden quantities that you would like to optimize, that you would like to learn, and epsilon k. And the classical assumption is that ak is known and epsilon k is a zero mean node. Okay. And our goal is to choose phi number of what I call measurement strategies. So you could imagine that in a simple case, it could be choosing phi features such that you are able to beat the best or the most accurate estimate of x. Okay. So I would like to know if some of you, perhaps in the audience or online, know that this is a problem and how to know perhaps more about the students, because I'm not sure we are teaching this kind of stuff anymore. Some of you know how to solve this or no? Okay. Okay. So how to solve this? So first of all, what you will do is you will just define a bit better what is the strategy. So you will define a vector W, where Wk is equal to 1 if the measurement strategy K is chosen, and 0 otherwise. Okay, so you have this big vector W, and we will just try to rewrite the signal of the following form. So basically, for a given vector W, you can rewrite your observation as follows. Y, which is just the concatenation of all the observation that you get when you use a set of measurement strategy, and AW, which is also the concatenation of all the observed matrices. Okay, and so this is your signal. And the question is, as you can understand, is as you can guess, is what are the WKs that you should put to 1, knowing that you can only put phi of them. Okay, so this is a classical question of experimental design. So in statistics, what we do in this kind of linear case, if we assume that the covariance of the noise is a diagonal matrix, then you can use the Gauss-Markov theorem, which is basically telling us that the best linear unbiased estimator is given by a pseudo-inverse. Okay. And also, you have information about the variance of this estimate. Okay. And the variance of this estimation, as you can see, is depending only on A of W, the covariance matrix, and the covariance matrix. What is important to also note is because you have an unbiased estimator in this case, and this is why when we will try to extend this, it's not exactly working. And you have also this assumption about the noise. The variance is not depending on the observation. Okay. It's just depending on a simple formula. So the question is, what can we do from that, right? So the first thing that usually people do is the variance. They will just say that we have worked in the noise and the matrix sigma is the identity matrix, you know, just by using some normalization. Okay, and then another thing that you can observe is basically AW multiplied by AW transpose, which is equal to MW, is simply equal to the summation from k is equal to 0 to n of WK and the observation matrix, the transpose of the observation matrix multiplied by the observation matrix. So what is really interesting now is we have a simple form for the matrix MW, okay, which is basically just a linear combination of the difference of a specific form of the observation matrix. And this is really powerful, right? Because now we feel that possibly we'll be able to optimize the variance. More specifically, we are interested in minimizing the variance of the estimate. So basically, the challenge, as I say, is to minimize the variance of my estimator. And this is the way I will select my features, is trying to obtain the minimum variance. The problem is, I guess, you know that this variance matrix, it's a matrix, right? So how do I optimize the matrix? It's not really clear. Because even if it's a symmetric matrix, you can have an ordering. There is a pseudo ordering in a symmetric matrix, but it's not enough because it's not a full ordering. So think of this variance as is that one ellipsoid can be contained in another ellipsoid, right? So you have some orders, but in some cases, if I put the ellipsoid like that or like that and so on, sometimes you don't have an order. Okay, so this is why we talk about pseudo order. So it means that we need to find a function g that will try to maximize that. In some sense, we capture the property of this ordering plus its property. So this function is called the scalar information function. And it has to satisfy the following property: positive homogeneity, the monotonicity with respect to the Lowndes ordering, where the Lowndes ordering is the ordering in symmetric matrices, and concavity, right? Because we want to be able to solve this maximization problem. So a typical example of G is just minimizing the smallest eigenvalue of the inverse of the variance matrix, or something related to the trace and so on. So you have a set of metrics, and when you see an experimental design, A design, D design, and so on, so this is things that perhaps you will see when you want to select features, it's just a different form of G. So basically, depending on the way you choose G, you choose different way of selecting features. Okay. Yeah.
So M here is the principal method.
Yeah.
So basically here, lambda mean of M is following a Reiffers-Masson with a regularizer.
Lambda mean is just the smallest eigenvalue. So is it?
So when you solve a Reiffers-Masson, generally you get a graph which is the precision matrix in terms of the relation, the shared elements of the and you have some regularizers from the sparsity of the precision matrix, which and lambda mean is the lambda two.
So the value. Okay.
Field vector. Field vector.
The vector. No, value, right?
Value, the eigenvalue associated to the vector.
Okay. So, okay, so I think perhaps your question is related. So it's nice that you give me J, but doesn't mean how to optimize it, right? No, okay. So it's just a link. Okay. So yes, true. In some sense, it's measuring the dispersion of your matrix, right? So using the spectrum. And basically, when you go to trace of M at the power P, and then at the power 1 over P, what you will have happen is you will not just maximize lambda mean, but you will maximize a linear combination of the different eigenvalues, right? So this is kind of the standard criterion when you do experimental design. So what about this problem? It has been proved that it's NPR. Okay, so it means that if you have a small number of features and you just want to use any classical mixed integer solver, you cannot go up to 50 features that you can set, right? Something like that of this order. So, however, we are able to say a lot of things because we're able to construct greedy algorithm, right? And greedy is just you select the best features, and then you among the n terms, you select the first best features, then you do it again and so on in this iterative way. And when you have good property, which is called submodular properties on your function, what you can show is that this algorithm is, I think it's something of the order 1 minus 1 over exponential something. Basically, we're able to give some property on how far you are from the object. So it's not because it's NPR that it cannot be solved. A lot of heuristic has been used. So greedy algorithm is one. And the other one is convex polarization using semi-definite programming and things like that. Okay. So it can be solved, but still in small problems, right? Even with good heuristic, be able in greedy algorithm, you have to understand that you have to compare what is impact of the strategy on every point, right? On every eigenvalue. And you see, if you do that a lot of time, it starts to be really expensive too. Okay. And also, there is classical issues, means that there is issues with this classical formulation, which perhaps for the machine learning community is not really of interest. It's, first of all, it's linear, A is known, you are able to have an unbiased estimator, and basically you need the Gauss-Markov theorem to make sense to this variance. You could always, sorry?
Yeah, just as a remark, it's not that useless in our domain, but I mean, for oceanographers that might be listening, this is optimal interpolation. Okay. Just wanted to draw that connection.
Okay, so actually, I think it's extremely relevant for a lot of things, because basically you try to control the kind of variance, but if you just directly minimize the variance of your estimator, it's not the best thing to do, because most of the time you have a bias estimator, so you will have to manage a trade-off. And here you don't care because you are only taking care of you have an unbiased estimator and you only have to manage the variance of your estimator, right? But of course, I think most of the time, the first thing to do would be to formulate this problem this way with a linear signal and so on, and see whether or not it makes sense in your context. This is kind of, and it's still working well, and there is a really beautiful theory behind it, and so on. So true, I will not skip it so much. So the questions that we have asked ourselves, and it's a bit also in discussion with Luca, is Luca, 2 weeks ago, I've introduced you to B-level optimization for hyperparametrization. And the question is, of this talk is, what can we do more using B-level optimization? And also, can we try to understand what are the feasibility and the possible performance of this problem? Means that even if I'm getting the best sampling strategy ever, how good I will be in a general context. And we'll try to develop some simple mathematical tools to answer these two questions. Okay. So is there any question perhaps online or now, or is it clear for everyone? Because it's kind of, yeah. No worries, it will be easy. It will be easy. So no question, okay. So first, how I will do my extension, it's just a trick that I'm using. But because if you really work with deep neural network and so on, it will just be really not so trivial. So we'll work with what we call random neural networks to do this extension. Okay, so I will first introduce what is random neural network. Okay, so assume that you have a probability distribution P on a given space, and you have what we can call a random function phi, which is taking your input and has a set of parameters. Okay, and you assume just to make the assumption work that your function is bounded by 1. Of course, you could put any other constant, but basically what we are saying, it should not be able to go to infinity. And you will define two spaces of function. Let's define the first space of function f of p, which are the ones that can be written as a linear combination, but in the Hilbert space, so basically in a functional space, a linear combination of phi of x theta multiplied by alpha of theta. And what you say is basically that the weight alpha is decaying slower than your probability distribution p theta. Okay, so it's just a type of function, and I'm interested in basically capturing this kind of function. So actually, we can prove that this type of function are dense among all continuous functions. So basically, it's kind of this class of function is including all the continuous functions that you can prove. Okay. And then we decide some kind of the approximated space where for a set of parameters theta from 1 to k, you just define the function f of x with which is equal to the linear combination of the phi of theta k, where theta is defined in some way. I didn't tell you how yet. And I'm saying that the norm of the weight are below some. Okay. So yeah. Okay. So what is really nice is we have the following theorem. You take a function f in your general space of continuous function, so f of p, and basically you have a probability measure on x, so basically on your input-output, on your input, and your parameters theta 1 up to theta k, so you have to imagine that it's vectors, are drawn from ID, from a distribution P, okay? Then what we can prove is that for all delta, there exists with a probability 1 minus delta, a function belonging to the space f of theta, so parameterized by theta 1 to theta k, such that the distance with respect to the measurement is smaller than a given constant. And what is important is to observe that the dependence in the square root of k. So what does it mean? Is the more you are sampling some parameter k, right, theta, the more you increase the number of sample of k of theta, the better will be your estimation. So what does it mean also is that we are able to approximate in a good way any function which belongs to the space f of x. So let's try to just go back a bit to what could be a random neural network in this case. Imagine that just f of x of theta is the output. You have your input x and you have your output, which is f of x of theta of your neural network. Okay, and what you simply do is every weight except the one of the last layer are drawn randomly, which correspond to theta. And then the alpha k is just corresponding to do a linear combination of the last layer of all the layers before, where all the parameters have been drawn randomly. And what is interesting and why people have studied that is, first of all, because even if it's not perfect, we are able to prove that it's converging. We can approximate any function in FP, right? And the second thing is that the computational cost, right? Because you don't need to do back propagation or anything like that. The only thing that you need to do is draw once all your parameters except the last one, and then just do a linear regression on your random kernel. So basically, it's a theory for what we call also random kernel. I'm drawing in a basis of random function my kernels, and then I'm just doing linear combination. And this is the kind of function that we can have. Okay. And for example, let's say that we have this time series. So the x-axis is the time and the y value is what we call a delay here. And you have this kind of time series with even a switch, more it's a really continuous time series and so on. And it's always the same time series, but what I've done is I've sampled 20 points among these time series, and I've just tried to learn my random neural network. So it's just 3 layers where all the parameters are drawn randomly, and the last layer is of size 21. So basically, I'm just doing the combination of 20 kernels, 20 random kernels. And what we see is what we see is it's interesting. So in some cases, it's working really well. So for example, here means that working really well, it's able to at least capture the trends. And in some cases, it's working really badly, right? Here, here, and here. So of course, the more I'm increasing the number of samples, the better it is. And I didn't put the theorem, but it's of the order 1 over square root of the number of samples. Okay. So still not great because it's square root of n, but we can do something. And this is also, this picture is really motivating why we want to do sampling and choose the best data in a time series, right? Because you clearly see that what you would like is to kind of recover the samplings that has been done here, or perhaps here, or perhaps, let's say here, but not at all this one, right? So it's also a justification for why choosing the right feature is important in this kind to make work this kind of work. So do you have any question for that? No. Because I see.
So just a quick question here. You don't show where you actually sample the points. So
no.
Can you, if you do something uniform, what would you get compared to all this stuff?
So in this case, it's a really good question. I think if you do uniform, it's uniform. Means that no,
it's uniform, but you regularly sample.
Regularly. So depending on your interval, the only risk that we have there, so it's a good question, is the only risk you have there is, I think, to miss the small part.
Okay.
Right, because you will just sample once there in comparison of the rest.
So it's not at all optimal to do that.
No,
there is some sampling
if the time series was a bit again regular, and if the interval were more or less the same size between jumps, most likely you should have done something like that, right? Because you have enough. Okay. So typically, why you have a problem here? Because most likely you nearly didn't sample here. It's just there. So you need to sample a bit everywhere. Okay. So how to model this problem a bit more specific? So what we have seen so far is first how to model the problem when we have an unbiased estimator. And now the question is how to model this problem as perhaps I will see. And so on. Perhaps you can do it.
Yeah, I think it was just an email. Sure.
Because I see that there is no application.
Pretty hard to do that.
Well, it's
do you have a question? Yeah. This is surprisingly hard to do.
Okay. So how to formulate this problem a bit more formally? So we assume that we have access to D time series. D, what I will call D data sets. And each data set is composed of high multivariate time series of length F. Okay, and I will just, so for now, I will just say that all these time series are basically of same size, and every data set has the same number of tests. Okay, to make it simple. Okay, and the data set is just denoted by a matrix X of. Now I will also talk about my optimization variable, which is a matrix W, which are a matrix of integers between 0 and 1. And the IK entry of W, denoted by WIK, is equal to 1 only if you want to observe in every data set the time series I at instant K. Okay. And it's equal to 0 also. Okay. And our goal here is to learn the best entry of every data set to observe, such that using a random basis model, I will be able to reconstruct accurately all the unobserved entries. So now we start with our B-level formulation, and I will start with the lower problem formulation. So we assume that, as I said, you have your random neural network, your random basis model, And you have access to a bounded feature function, phi ik theta, where phi ik are your inputs. So basically, the index of the time series and the instant, and you have a parameter theta, right? And you can draw your parameter from a given distribution. And you have two parameters. You would like to learn your regression parameter, alpha, okay, your vector alpha, and you have also a regularization parameter. And to estimate the unobserved entry of the different matrices, we'll just solve a regression problem. But first, what we do is we first generate our basis of random function. So we generate m sample of the vector theta from the distribution P of theta. And then finally, we solve our regression problem, which is just a classical regression problem, where you try to learn the best way alpha to fit your random basis to the observed data. This is why it's multiplied by WIK. And you have your regularization parameters that allow you to generalize. Okay. So this is your lower optimization problem. And because it's a strongly convex optimization problem and smooth, you know that the first order optimality conditions are enough to solve your optimization problem. And basically, you have to solve this equation. So alpha and star, you have to solve this linear optimization problem to optimize, to find the best regression. Observe that when I compute alpha m, so my best regressor, depending on WIK. So basically, depending on the data that I'm observing, right? Okay, so this is the first observation. So what I have to add also is, because we are in some kind of applied problem, it's important to say that you cannot just sample every data. And you can imagine a lot of constraints. The typical ones that you can think of is have a budget on the number of time series that I can sample per time unit. But I could also imagine some constraints of switching, right? I don't want to sample a time series that I've just sampled T units time ago, something like that. So imagine that you have a set of constraints in which W is belonging to, but it's convex set. Okay, so now what is our meta optimization problem? I'm trying to optimize my matrix W, which is which point I observe in my data set, to optimize a given cost, which is depending on alpha, basically my regressor. I'm not saying yet what is the cost. We will discuss a bit about it after. Under the constraint that W is belonging to my sampling constraint, and alpha m is solution of this if solution of this fixed point equation. So I think it's important that I stop here, and please, everyone should tell me whether or not it's clear the definition of problem. So basically, the intuition of problem P, I'm trying to optimize the function of my regressor, knowing that my regressor is depending on the data that I'm feeding it. That's all. That's it. Okay. Is it good also online? Well, I guess if nobody is asking a question, it's good. Okay. So now let's try to discuss a bit about the cost that I can put there. A standard cost would be, I know for every data set what could be the optimal weight. For example, if I have access to all the data, I could just compute the optimal weight alpha, the optimal regressor on my entire data set. And then I can say, okay, I would like to be as close as possible to this. Okay, so it's a classical solution in a supervised problem. Another solution, which is also a supervised problem, is that I would like to maximize my reconstruction, right? So this one is much easier than this one. You can already feel why, because we have much more things to compute there. So right now, I'm just trying to reconstruct in the best way possible. And so another one that can also be interesting is I would like to minimize my reconstruction on the unobserved data. And this one is really tricky because you have a dependence also on WIK, right? And this can be risky because perhaps you will be also, if you are not careful and your data are not normalized, tempted to also choose the point here that don't have huge spike of energy, right? So it can be also a bit dangerous to discuss. So if one has to use this kind of stuff, it would be better to work with the supervised setting, this one or this one. In the unsupervised setting, it's much less clear what to do. So I think it's kind of application dependent. And to be honest, I don't really have any ideas on what could be a good cost in the unsupervised setting, but we could discuss about it if you're interested. Okay. So the problem of, we have a formulation, we have an optimization problem, but the problem is even with the simple code. The first one, this problem is highly non-convex. Two reasons. It's a mixed integer programming, and it's non-linear. Okay. So what we could do is we could even try to relax the integer programming constraint into interval constraints. So you know your integer constraints are 0, 1, choose between 0, 1. But then you can just say, let's pick our value between 0 and 1. Sorry, in the interval 0, 1. But the problem is, in this case, the problem is still highly non-convex. And the reason why is because in the constraint, you will have term of the form WIK multiplied by the regressor. And the problem in D-level optimization, and perhaps Luca did not emphasize so much about it, is actually you have to optimize. When you will do the optimization at the upper level, you are also optimizing on the lower level. So it means that when I will solve this problem, I will solve at the same time WIK and alpha n. And you see that this kind of stuff, most of the time, it's not convex. Okay. Okay. And it is really in the best case. When you use all the losses and so on, it can be much more terrible. Okay, really good. So one solution of to solve this problem is to use what people in operation research call the relaxation using mixed logical programming, or the big M method. And what you simply do is you define an extra variable ZIKMD, which is equal to the variable, the terms that are creating nonlinearity, WIK multiplied by alpha MD. And you define this variable for every IK MD. And you have also to assume that your regressor is bounded. Well, worst case scenario, you can always put some really big bound. And by doing that, you can linearize your constraint by the following constraints. So I will not go too much into the detail now if you are interested in showing it, but it's just, we are just formulating a or condition. If this is happening, no, if and else condition. If my WAK is 0, then Z is equal to 0, and if IWK is equal to 1, ZIKM is equal to alpha. So this is just what we are doing by using this kind of constraint. So I would like to know if someone see already a problem there. So I will tell what one of my colleagues just said. Okay, nice, you have been able to do it, but you have a lot of constraints, right? Because you can observe that at least you will have this number of constraints, at least multiplied by 5. But let's say we don't care about the multiply by 5.
Can you give an order of the number of constraints in the case you were talking about?
So for example, for me, when I've tried to implement this thing, let's say that I is equal to 1, okay, to simplify, M is equal to 20, D is equal to 1, and N is equal to 100. So you already see that we have something like 2,000 constraints, something like that. And this is really, I've killed nearly all the parameters of my thing. So you see that the problem is polynomial. And the problem in machine learning is typically always this scaling problem, where actually you have your data set are big, your time series are big, and for example, putting M, which is the number of random kernels that I'm using, means that for my problem, it will work, but I'm not even using the power of random neural network, right? So now that we have understood that, yes, you can solve this problem, you can write against this problem with linear constraints, but it's still a Dixit-Tanger problem, but we could have hope, but there is just too many constraints, right? And the question is easy to solve this problem? So branch and bound, not possible. Because there is just too many variables and too many constraints, right? Because the order of variables is about 5,000, for example, for a simple problem. Convex relaxation, so you could hope that it works, but in this problem, it's not working because you are giving too much power. The moment you start to relax an integer constraint into an interval constraint, in this case, it's not working because what we suspect is that there is too many global optimum, right? There is just too many of them. There is too many possibility, and therefore it's not working. And therefore, just solving this simple problem is, and finding a way to solve is an open problem. At least for us, we don't know a good way of solving this optimization problem. And kind of the takeaway that I'm trying to give you with this one is, yes, B-level is nice, and even doing a bit of optimization and operation research is nice, but be careful to the number of variables that you are trying to optimize. Yes?
And repeat question.
Yeah.
The problem is the number of constraints or variables.
No, it's not even that. I suspect it's in the linearization that I use. So I think the problem, if you want really to go into the detail, is when I decouple this multiplicative term. So for the branch and bound, clearly the number of variables and both of them kind of completely are over the top. Not make it even work well for the convex relaxation. So I'm obtaining a solution, but then I don't know from the convex solution how to go back in a smart way to the discrete space. And every method that I've tried are just bad. And
yeah, what is the dimension of the problem?
so time series of 100 points and a random neural network. So basically you have to choose 20 points among 100. So perhaps this is also, at the end, it's already a hard problem, actually, when you think a bit about it, because combinatorial is already bad. And the dimension of my neural network is, of the number of random network is between 20 to 40.
Okay. So can you assume that some of the constraints are useless and then try to randomly sample constraints and solve the problem in a less constrained way and do it for multiple realization of constraints?
Yeah, okay. So my point is there is perhaps a lot of smart way of trying to deal with that. But the question is, we have seen that on my problem, random sampling is already doing quite good in some cases. So you like to have an algorithm that is at least beating random, and it's not even clear. We could try that, definitely.
Isn't it some kind of branch and bound, basically? Trying to select some constraints that are inactive and go explore some kind of combinatorial tree inside that?
Yeah. Yeah. But the question is, you see, even to have an optimal value of this problem, for my problem, if I just put it in a public solver, it's taking too much time. It's not even interesting. And even greedy solutions are not great and so on. So I think the takeaway of what I'm trying to say here is we can write a lot of nice mathematical relaxation and so on, but when you are really trying to make it work, actually it's hard. Yes.
When you're doing relaxations like that, replacing integer variables by interval variables, are there ways, I'm not familiar with this, to quantify how far the relaxed problem is from the true problem?
Yeah, there is. Yeah, yes, there is. No.
I mean,
I don't know how easy it is what you're suggesting, because basically when you are an integer problem, you are working at the corner of your polyton, right? And what you are saying is it possible to quantify when I'm not restricting myself to the corner of my polyton? polytope. And the problem of the corner of polytope, not every corner of your convex polytope is an integer point.
Yes.
So then it's becoming just discontinuous. So I guess people have been able to prove for shortest path problem, things like that. But usually if you want to do such things, what you should do is try to frame your problem in a well-known problem.
Yeah, the only example I know is the sparse regression.
Exactly.
L0 norm, 2L1 norm. In that case, we can say things, but in the general case, it not be super hard, I guess.
Yeah. So there is also people that work on randomize in thresholding the convex, for example, when you compute eigenvalues, and then you want to go back, you know, eigenvalues problem on graph are equivalent to cutting your graph, right? And people have tried to work on how to go from eigenvalues to cutting again. And usually they use some kind of random, to go back, random relaxation and things like that. So I'm not familiar with this technique. But usually, if you would like to tackle this problem, you would say, I'm solving some kind of eigenvalue problem, and then I'm using this kind of technique. So I think you have to fall into a classical problem first. And clearly, for now, we are not falling into a classical problem. Perhaps I missed something, but and also what is really scary is still when you think about it, choosing k points among n is a hard problem. Actually, it's not so trivial. It's not like choosing 1 point over n or 2 points over n, right? Okay. Okay. So still, we will push towards this problem, because there is actually a lot of interesting stuff that were interesting. Because what is sad is this problem is kind of the baby version of what we really would like to do, right? In reality, what we would like to do is minimize an expectation, right? We don't want to minimize the empirical risk. We would like to minimize what we call the population risk. And the way to do that, you have a simulator and you assume that you can sample infinitely points in your simulator. And therefore, in this case, you have to rely on online algorithm and things like that. And just working with that, what is happening is you start to have a problem with constraints which are belonging to an infinite dimensional space, where the scalar product is just determined by the distribution. I continue the presentation. Yeah. Okay. Okay. So what we have seen so far is how to formulate the problem. So now the question is a bit more simpler, is can we just develop a theory to understand for a given sampling how good or how bad we are? Perhaps I can just wait. What do you think?
It's recording, so
okay. Okay. So to do that, I will need to introduce two more tools. So first, before I'm going there, is there any other question about the B-level optimization problem in the audience?
So I guess maybe you can emphasize, as you said it, okay, what makes it harder than like a nested problem?
That, for example, the ones that you have seen. So
yeah.
Okay. In your case, there is two things. So in your case, you have only optimized one parameter, right?
Well, yeah. In the simplest case, yeah.
In the simplest case, and then also it was a continuous parameter. It was not a discrete. So this is already two big things. And actually, you said that to us, right? That you have tried to learn a neural network inside the lower problem, right? I mean, no, to train a neural network to learn the optimal parameter for every data set, and you did not succeed.
Well, I tried replacing that parameter by the output of a neural network, and then it wasn't working anymore.
But perhaps it's also the same kind of reasons that it's highly nonlinear and so on. And when you take the differentiate, the gradient, actually, the gradient have weird values and things like that. Okay. So now I will talk a bit more on how to just evaluate the performance of a sampling scheme, because perhaps for those of you who are coming from machine learning, you actually just want to make it work. But from my background with more operation research and perhaps kind of economic analysis, sometimes people were asking me, but is it just even possible? What kind of performance can be expected? So I'm always asking myself this question is, can we try to quantify that in simple models to see whether or not there is proof, right? So to do that, we will introduce stochastic approximation scheme. So stochastic approximation, I think all of you know this kind of scheme, which is simply, you say that you have a set of parameters that we will call W, and you try to learn the best parameter, right? And how do you do that? Usually it's using kind of a stochastic gradient descent. I will just stop for. Can check if there is some.
Yeah, let's check.
No, there is not.
Maybe you can explain.
I will explain
the relationship between this and stochastic gradient descent.
I will.
Yeah. Okay, it's on the slide.
I will do it. So, imagine that you have a stochastic gradient, right? What would be the update here? It's just a gradient of a given function, right? And what you just do is you go down the gradient. Okay, you follow the direction of the gradient, or minus the gradient if you realize. Okay. And usually these schemes are iterative schemes. Why so? Because you want to do cheap updates, right? Computing a gradient can take a lot of time, but it's not like finding the optimal solution everywhere. And also you can stop at any point of time your algorithm. So this is kind of the two really powerful things with stochastic gradient. Okay, and I've just added this kind of projection operator there to say that my operator should be, my iterate should be bounded. Okay. So so here is some technical assumptions that I will skip, but what is fun there is when one wants to analyze a stochastic gradient algorithm, one way is to just look at the associated ODE. So for those who are familiar with ODE, right, you can notice that my scheme, my stochastic approximation scheme, is nothing more than kind of Euler discretization of my ODE with a decreasing step size and with some extra noise. You can see at least the link between the two. And what does it mean? It means that when we want to analyze the convergence of the gradient descent, what we can do is we can prove that as long as you're understanding when the behavior of the ODE, the limiting behavior of the ODE, W dot is equal of H of W, then you can just transpose the convergence property to your stochastic. So this is what we call the ODE approach for gradient descent. And in some sense, what I'm also trying to say is when I want to study iterative optimization algorithm, before even going to the complex stochastic gradient or other scheme, what we usually do is we try to first understand well the property of the ODE, which is usually easier because you don't have noise and things like that. Okay. Okay. So now I gave you a small introduction. So the question is, what is the link with the sampling problem? So let's remove the geographical dependency, and we just want to sample a time series in time. Okay, so really simple problem. Yeah, no. Okay. So our control now of is not WIK, it's WK. And our data set is not XIK, right, but just XK. So it's just a time series. So we again have access to a random neural network, but this time the output is not also the location of your measurement, it's just the index in time. Okay. And we need to define this extra vector B, but it's just when you write the math, you will need it. So when you try to solve the regression problem, what are you doing? You are just doing a gradient descent. Well, in the case of the classical regression problems that we have seen, you can actually solve directly, but remember that when you compute a pseudo-inverse, usually you have an iterative algorithm here. So in some sense, you can just do this gradient descent algorithm, right, to find the best predictor. And the associated ODE is the following, right? According to the theories that I've just. And what you can observe is that, first of all, it's a linear ODE in alpha, right? And second of all, it's depending on W, which is my sampling strategy, and my data X. And what is also interesting is you see that the data is affine in comparison of alpha, right? So this is two really important observations. Okay, so now that we have this ODE, I will show how to use what we know, even I think any student in, that have done first or second year of math or I don't know, physics will know how to use this ODE to already give some intuition of how good or how bad is the sampling strategy. So we can, what is really nice also is giving us a theoretical framework which can help us to answer multiple questions. And I will for now ask myself 3 questions. The first one is, how good can be my sampling strategy? So basically, I'm working on the same ODE. And what is the best that I can do if I have a limited number of samples? So how to do that? I just need to compare 2 ODE together. The first one is the ODE with the actual sampling strategy, right? With the W and W. And what is the best thing that I can do is when I give all the data, right? So this is one here, and the WK here has disappeared. So now what we will just do is we'll try to compare the trajectory of these 2 ODE, the one under the sample W and the one with when we give all the data, and we'll compare them. And what is nice is in this case, everything is linear. So someone knows how to, well, I've written it, but there is a way to compare two linear systems. It's just by using the variation constant of method. And what we'll have is we will have that alpha t is nothing more than alpha opt, the optimal solution, plus exponential a given matrix, which basically A is this one, okay? And the error, the difference between just these 2 terms, okay? So the drift, the difference between the 2 drifts, okay? And what it is telling you is basically the distance between alpha t and alpha opt, in some sense, is controlled by, we have a formula which is, because these 2 are matrices, which is only depending on the drift, and therefore you can directly see what is the impact. So I will not go too much into detail, but first is you notice that if this is equal to 1 everywhere, so basically we give all the measurements, the 2 trajectories are the same. So in some sense, it will help you to just derive an error on the trajectory really easy, kind of for free. And so how can it be used in this context? For example, you can assume that you are sampling W randomly, right? Then you can just compute the expectation of the error and you will see how good or how bad it is. And you can find an upper bound. You see that your error is controlled by basically everything is in this matrix, B of X of P and this, right? So you can assume that perhaps you have a bit of extra information on your data, which is kind of give you the best thing to do at this level. But not exactly, right? You can compute what is the impact of your error. Okay. So now we will see how to tackle another problem. Now, the other problem that will be tackled more or less in the same way is what is the best sampling strategy to be able to transfer the learned weight on a new data set. Okay. So again, I will just write my 2 OD. I have my alpha train where I'm training my weight, right? And I will train a given weight with my dataset X train. And I have alpha test, which is assuming that I'm using the same sampling strategy. And I'm giving the dataset test. What is the trajectory? Okay. So this question can be formulated by just comparing these 2 OD, right, again. And what we have again is using the variation of constant method formula, an error, which this time only depends on in some sense, the difference between the data set and also your kernel. So what is interesting in comparison with classical experimental design, in some sense, you are only interested in the property of phi, the dispersion of phi. And here you see that because you have this bias property, right? You are not unbiased. You will always need to work with your test and with your data, your signal. Yeah.
In the previous slide, you were comparing the solution that you get for a given sampling to the one where you sample everything.
Exactly.
But in that case, okay, you don't have basically anything to solve. So
it's just to give the performance. How good I will be compared to the case where I give everything.
So but the DOG in that case, it just starts from some point and converges to the true solution.
Yeah.
Okay, but basically the DOG is trivial, right? When you sample everything, you know that it will converge to your data, your ground truth.
Your true alpha. But if it's biased, because I didn't put, you don't converge to the true ground truth, because remember that in random neural network, your signal is an integral of alpha W, your kernel.
Mm-hmm.
And what you do is you do a finite approximation of this integral in some sense.
Okay. So
you have this bias term which is still there.
Okay.
So to do that, you need to increase K.
Yeah.
That's the number of kernel functions that you are taking. So it starts to be a bit hard. Okay. So this is in some sense telling you how to do transfer and what is the performance of transfer in this context. And finally, imagine that, no, I went a bit fast, that I would like to do the same thing as transfer, but I have an extra constraint. I want to compare what's a sampling strategy when the time series are not of the same size. And I would like to transfer my weight because the size of the weight will not change. It's just that the number of data and the type of data that I will give will change. To do that, I will add an extra function G, which is telling me how to, for given sampling strategy, for example, on of a time series of a given length, how to make it go to a time series of a different length, right? So this is my function.
Can you just explain what's the practical interest of being able to do that?
Because actually, okay, so that's a really good question. Actually, in practice, why we're trying to study the scaling stuff is that when you will work in optimization of every practical problem, or just working with a simulator, you are able to generate points, but in given configuration. For example, I'm able to study I'm able to generate some time series in a small graph. But in reality, my graph is much larger. And therefore, I would like to be able to study the transfer property because generating a point on a large graph or a time series on a large graph is extremely expensive. So this is why people study zero shot and so on. And right now, I'm not even talking about zero shot. I'm just telling when can we do this transfer? Okay. And so basically, you have again two linear OD to compare. And this one is a bit more tricky. So this is why also I say do it yourself. But it was not so easy to derive in one way. But you can also study the error and see how to optimize lambda and study different samples. Okay. So all these methods that I've just introduced, the OD approach can be used to basically understand better the performance of the different sampling approach and tell you what can be done and what cannot be done. It will not, and perhaps it can guide you in your choice of algorithm and sampling algorithm, but it will not really tell you, it will not guide you so much in creating an algorithm. It's more about feasibility of the problem, right? What can be achieved, at least. Okay. So right now, with random neural network, I've cheated a bit because everything in some sense is linear. You have random basis, but you work with everything which is non-linear. But actually, it's not a problem because to use the OD method, the stochastic approximation theory works for nonlinear function, right? So it's okay. And to study this kind of variation, you have two theories to look. First is what we call the Alexis formula, which is an extension of the method of variation of constant variation to nonlinear case. So you can basically do the same thing for nonlinear case. And if you have something which is non-differentiable and so on, you will have to look for what we call perturbation theory, regular and cellular in differential equation, which will not give you practical bound, but will give you the order of the bound. Okay. So kind of the conclusion is of this talk, we have seen how to reformulate as a B-level problem the optimal sampling problem. And at the end, we see that we can reformulate as a mixed integer quadratic optimization problem. So what is the positive point of this thing is that a convex relaxation exists. So we would hope that convex optimization will save us there. But for now, there is too many variables and constraints, so we have to be a bit more smarter. So it's not working well. And we have also seen how to use the theory of OD to study the performance of a given sampling strategy for transfer, for optimality, and so on. And the possible extension that we are currently working on is because in such context, our time series and the data coming in batch every day and so on, and the environment can change, we cannot rely on just studying on one data set. We are obliged actually to use online and adaptive algorithm. And this is why we went to observe a bit convex optimization, because we know that if we have a convex problem, we should be able to solve this problem. So this question is still open, how to do online and adaptive. And also, for now, I've just used really simple tools to study the property of a sampling, optimal sampling problem, but it would be nice to have a more robust theory. So that's it, I think. That's the end of my talk. And yeah, of course, make it work in practice on real problem is kind of the big challenge. And here is kind of the materials that I use.
Thank you, Alexandre. Any questions?
No.
No? Okay. Online, maybe?
I'm not sure. I don't think so.
Okay.
I have one about.
So you've presented a lot of different tools that, if you're not familiar with all this, with the problem, they can all tackle this problem, but they're all very different. You've tried a bunch of them, and what would be your best hope to solve this kind of problem? What is the most promising to you among all those techniques?
Okay. So there is two aspects of it. I think what looks really, really interesting to me is I have two sampling strategies. I'm not trying to find the optimal one. I have only 2, 3, 4. And I would like to understand in which context the best what would be the best. And I would like to understand the performance. I would really use the OD approach because it looks really exciting and kind of easy to say some trade-off, like this one is much better than in this case if the noise is like that and things like that. So I would not try to find the optimal sampling strategy. I kind of have lost hope with that. Because finding the optimal strategy, first of all, what does it mean to be optimal? It means that you are optimal on one particular problem. It doesn't mean that when you extend, you generalize. How to generalize is already hard, and perhaps random is already doing really good in this context, right? If your data is changing a lot and so on. The second thing that I would say is sampling a signal in this context is really something random, right? Because your noise can change and the jump can change and things like that. So I would go more for a random sampling strategy and perhaps try to optimize the parameter on. I would sample according to a given distribution, and I'm trying to optimize a bit the way I'm sampling to improve my strategy. I would not go for deterministic sampling because I think it's not, I'm not even sure it can generalize. And it's also, I was having some hopes that it would be easy to solve it's not even easy. So kind of what is the problem?
Another question, maybe. So for people who have seen a bit these kinds of problems where two levels, etc., there seems to be a clear connection with optimal control. You haven't talked about it. Can you tell us how it fits into all these methods?
Oh, it's really good. Actually, it was a third part of my talk, but I was like, I will not have time to make it digest. So optimal control is kind of a natural framework. How? Assuming that you want to do adaptive learning, right? So if you do adaptive learning, what is the classical trick? You assume that your data is changing slowly over time, right? You need this assumption, otherwise just you cannot do adaptation. And what you will do is you will run at every iteration, you will take the new bunch of data and you will just do a bit of, you will just do a small 10 iteration of gradient descent, and you will not do more, because then you start to specialize too much to your data. You do that multiple times, right? And you alternate. Every day I'm taking my new data and I'm training just 10 steps, and so on and so forth. So when you do that, actually this is called tracking. And we can use the OD theory to have the error between the estimate and the true signal. We can derive error, and we can actually, so it's depending on Lipschitz constant and things like that, but you can actually have some nice form of the error. And when you do that, you can ask yourself, okay, I have a nice form of my error. How can I optimize over time? In some sense, you will try to track if your error is going really high. In some sense, it will be okay, good. Now it's time for me to sample more data, and so on and so forth. So how I would formulate the optimal control problem, I will go to the OD. I will try to find an error a formula of the error which is not requiring too much information about my signal, but a bit, perhaps the variance and the mean, for example, something like that. And then what I will do is and derive an optimal control problem. So it's kind of the next step, but you need, I think, the particular problem where you can actually estimate all the quantity.
Okay, thanks. I don't know if there are.
Yeah, question.
So you have time dependencies in
Yeah.
your first part. So what is your first time dependencies between time?
Really good. So initially you have space dependencies. In the V-level problems that we were talking, you have time and space dependencies. And it's not actually just because of the space dependencies that the problem was hard, even just in time it's hard. And in this problem, I've killed the time dependencies, but just to make the presentation digest. It's not changing anything. You can do everything with space dependencies, and you just have to compare to sample space.
But how did you model the space dependency? Because you have multiple data sets.
So I just say that my time series are depending on a label, a position I and an instant, where I didn't say what was my position I. So we
You don't have any instant metrics between the various types?
No, I didn't. It was fair enough. I know what you want to say, but with the end. With the end. I just say that. I didn't say the model and so on. I just say that there is a model that if you give the location and the time, this is my neural network. Location and time, and I'm able to predict.
So there's a continuous representation underlying somewhere.
Somewhere, not clear where. So the ordering is actually, if you just take time series like that, it's really dangerous, right? Because depending on the order of your index, it will not work. So, but in some sense, we could add the random neural network and so on has been extended to every context, right? You can also do that in graph neural network. You can do that in CNN, and so actually for students who want to see a bit of theory of neural networks, this is also just an advice, is when people want to study the performance of a neural network, usually this is what they do. They say, we assume that the width of the layers are huge, and in some sense, it's equivalent to say that all the weights are random except the last one. So the theory of random neural network has been used as an easy way to interpret the expressivity of neural networks. And they have done it for everything. So they have done it for CNN, they have done it for recurrent neural networks, they have done it for everything. So there is a really good tutorial at the end of the talk. The good tutorial on random neural network is this one, where you have all the papers, and you just write actually a random neural network, deep random neural network, and kind of the results that are presented that are kind of cute and still it's the baby version and easy to read is this paper, weighted sums of random kitchens.